Okay, so let's talk a little bit about here, chapter 9, and stoichiometry. So first off, really important with stoichiometry is the equation. And when we look at the equation, there's a couple different ways that we can look at a balanced equation and determine, sort of what we are dealing with. And really, most of them do involve just the coefficients. So that's a 2, that's a 1, and that is a 2. One relationship that we could say is for every 2 molecules of H2, it reacts with 1 molecule of O2 to give us 2 molecules of H2O. For the second one, which is really when we do stoichiometry, it's really sort of the relationship that we use. And that is what is sometimes referred to as the mole to mole relationship. For every 2 moles of H2 reacts with 1 mole of O2 to produce 2 moles of H2O. The mole to mole relationship really is just the coefficients from the balanced equation. There's no sort of calculation to get those relationships. It's just simply the number. The last one is one we don't really use too much, but it's a reminder of sort of the conservation of math and sort of why we balance everything. If we started with 36 grams of reactants, we should end with technically 36 grams of products. And what that means is obviously when we balance the equation, for example, here we have 4 hydrogens on the left and 4 on the right, which means hydrogen's 1 gram or so there on the left and hydrogen would be 1 gram on the right. So because we don't lose any elements along the way in a chemical reaction, we should have this same sort of molar mass on both sides. So let's talk a little bit about stoichiometry. And we use stoichiometry, like I said, to answer a lot of questions about a reaction. If we pretty much know kind of just one piece of information about somebody in the reaction, we could pretty much figure out how everybody else there would maybe we started with or ended with. So for example, if we know just one of the reactants, how much we started with, we could figure out how much products we should produce if everything went perfectly well in the reaction. Same thing going the other way. If we actually just know, maybe how much of one of the products that we made in a reaction, we could actually kind of back calculate and figure out how much of the reactants we started with. So stoichiometry allows you to answer those questions. It also allows you to figure out technically the theoretical yield, which we'll talk about, which is really the maximum amount of product you should produce in this reaction if everything went perfectly well. So when we do stoichiometry problems, frankly, the units can really be anything. And as we go through some of these later chapters as well, we'll see stoichiometry again. So in this chapter, for the most part, grams and moles is sort of what we'll see the most in terms of units. But we can have other things like when we get into gases, it's very common we use liters. Also, when we get into solution, molarity is another unit that's commonly used along with volume. But the basis really of all sort of stoichiometry is, regardless of sort of the units that you start with, pretty much one of the first steps that you do in a stoichiometry problem is turn those units into moles. So that's kind of like almost like really the second step in pretty much all stoichiometry problems is pretty much whatever they give you and whatever units they may be in, you pretty much need to get it into moles. And the reason for that is really the stoichiometry part is a mole to mole sort of relationship. That way all the units really cancel out correctly. So for a lot of these calculations, we will fall back to what we talked about earlier, that we will definitely do kind of a gram to mole conversion, and a lot of times moles to grams at the end. And again, it is that molar mass from the periodic table that allows us to do that conversion. So that sort of conversion of taking grams to moles, and on the back end of these calculations, a lot of times you got to go moles back to grams. Using that molar mass is, again, something that you use a lot. People sometimes overcomplicate stoichiometry thinking it's really sort of a very difficult sort of idea. It really is just, and it's really, the difference is instead of going to a table to sort of find your conversion factor, where you find balance equation. So that's just basically what it is. It's nothing more. The stoichiometry step, it's just a simple conversion using functional analysis. In a lot of these problems, you're given information about somebody in the reaction, actually find out, somebody else. Maybe you're given something about the reactant. You want to find out how much product. So you need a way to go from like the reactant to the product, or vice versa. Maybe you're given a product and you need to figure out how much reactant, or even between reactants, or even between products. So where we find these sort of conversion factors is from the balanced equation. These are some basic steps that really can, a lot of times in basic stoichiometry problems, be boiled down to kind of 4 steps. This is assuming that step number 1 here, that you actually don't have the actual equation given to you. So maybe you have everything in words. So occasionally that does happen. You're kind of given everything in words. So you do want to make sure that you turn sort of those words into the proper formulas. So as we talked about when we talked about balancing, it's really important to make sure that you start with the proper formulas before you start to balance it. So you want to turn everything into the proper formulas. Then you want to actually balance the equation, which is really the most important thing here. If you do not balance the equation, pretty much your whole calculation is going to be off. So I would say probably 9 times out of 10, you will be given the equation. So you do want to just make sure that you take a look at it and make sure that it is balanced. I would also say that if you see coefficients and numbers, it's probably balanced unless they're trying to trick you. But in most cases, it should be balanced. But if you don't see any numbers in an equation that's given to you, you definitely should take a good look at it to make sure it is balanced. And if it is not, that you actually do balance it. The next really main step that you should do after you get the balanced equation is, as I mentioned before, take whatever they give you in whatever units it's in, and basically convert it to moles. So very commonly, grams is kind of where you start with that, but it may not be grams. Maybe you start with pounds or something like that. You got to do a couple conversions to get it to moles, but you basically want to get everybody into moles. The next thing you want to do is actually the stoichiometry part. So the stoichiometry part is you go to the balanced equation, you find the relationships, which is the mole to mole relationship, which is nothing more than the coefficients in front of the 2 things you're interested in. And you come up with really a conversion factor that allows you to go from, say, the reactant to the product. Once you do that, the very last step in a basic stoichiometry problem is you will always be in moles at this point. So after you do sort of the stoichiometry part of the calculation, you should always be in moles. And a lot of times you do not want the answer in moles, so you need to convert that to some other unit. So you would convert it into maybe grams on the back end using the molar math. So let's take a look at an equation such as this. So if we have an equation like this, which is balanced, we can really come up with several relationships to this equation, and they're what are referred to as mole to mole relationships, are being stoichiometrically equivalent to each other. We could say, for example, for every 2 moles of CO that I put in there, I will also need to put in there 1 mole of O2. And those numbers come from just the coefficients in the balance equation. So it's basically those coefficients. We could also say for every 2 moles of CO I toss in there, I will get 2 moles of CO2 out. And we could also say for every 1 mole of O2, I will also get 2 moles of CO2 coming out. These are 3 what are referred to as being stoichiometrically equivalent or qualities. They are not equal to each other, obviously, in terms of numbers. Obviously, 2 does not equal 1, but they are equal to each other in terms of proportion of what you need to toss into this reaction, basically, for it to take place. Again, kind of like you cooking cookies, right? You need so much of all the ingredients to get a dozen cookies. So you got to toss this right proportion of all these guys in there. But because they are technically equalities, stoichiometric equalities, we could actually write two conversion factors for each of them. So for each of these sort of equalities, just like we were doing when we did way back there at the beginning, conversion factors and equalities, we could write two for each of them. So for example, for the first one there, we could write 2 moles of CO over 1 mole of O2, or we could write 1 mole of O2 over 2 moles of CO. We could also write 2 moles of CO over 2 moles of CO2, or 2 moles of CO2 over 2 moles of CO. And lastly, for the last one there, 1 mole of O2 over 2 moles of CO2, or 2 moles of CO2 over 1 mole of O2. So from this one sort of balanced equation, we actually have 6 different conversion factors that we could use in a problem. Just so we're clear, you won't use them all. You obviously will use just the one that you need. But these are all the sort of relationships, the stoichiometric relationships that you could get from this equation. Any questions on how I got any of those there? So for example, if we were told that we started with, say, 12 grams of CO2, and we wanted to know how many grams of O2 did we start with, we could really just follow those kind of steps that we talked about. And as I mentioned before, we really could boil those steps down to 4 basic steps. The very first step is you want to always make sure that you have a balanced equation, which obviously here we do. So that part is good for us. The second step is you want to convert whatever they give you into moles. So in this case, the only piece of information that they gave us was 12 grams. So do I need to convert that into moles? I do. It's in grams, right? So we do need to get them into moles. Otherwise, the stoichiometry part doesn't work. So once again, to convert grams to moles, we go to the periodic table, and we would need to get the molar mass here of CO2. So if we do that, and we go to the periodic table, CO2's molar mass should be 12.01 grams per mole for our carbon, plus 2 times 16 grams per mole for our oxygen gives us 44.01 grams per mole as the molar mass. So really the second step that we're going to do here is going to take the grams that they gave us of CO2, and we're going to use the molar mass, and we're going to convert it into moles. So 44.01 grams per mole of CO2. And if we get an answer at this point here, that's 12 divided by 44.01, gets us 0.273, I'll take it there, moles of CO2. Any questions so far? So this is just like, we talked about grams to moles, just a grams to moles conversion. The purpose here is just to get it in the right units, because the next step is really the stoichiometry part. So this is the big stoichiometry step, which is step number 3 in most of these sort of equations or problems. And that is the mole to mole relationship. So you get that from the balanced equation. And the reason we need to do that is if we think about what was given to us, we were given information about CO2, but we're really interested in the end about O2. So we need a way to go from CO2 to O2, and that is really where the stoichiometry comes into. So this is really all it is. It's just a conversion factor. So what we would do is we would go to our equation and find the mole to mole relationship, which we did a second ago. And it is this mole to mole relationship right there, right? For every 1 mole of O2, we get 2 moles of CO2. And once again, it is just the coefficient. That gave us these two conversion factors down here. So basically what we want to do is choose the conversion factor that's going to, in this case, get rid of CO2, which we're not interested in, and leave us with O2, which we are interested in, which means if I had to choose, I should use which conversion factor, the one on the left or the one on the right. So once again, we want to get rid of CO2, which means CO2 needs to go opposite, right? Which means we actually need to use this conversion factor here. That's going to do it. And this step right here is the big stoichiometry step. We're going to do 2 moles of CO2 on the bottom, 1 mole of O2 up on top. That's going to allow us to go away from CO2 and get over to O2, which is what we're interested in. So in this case, we'll do a little dividing by 2, 0.136. Any questions on that there? Now, at this point, if the question asks how many moles of O2, we would be done, right? We could put a box on it. But in this case, we really don't want moles of O2. We want grams. So the 4th step, which is commonly what you need to do, is now take these moles back to grams in this particular case. So the 4th step here is to convert moles to some other unit. And again, a lot of times it may be grams, but it could be any other unit at the end. Maybe you need to do 1 conversion, 2 conversions, however many conversions to do so. If I have moles here and I want grams, I once again need the molar mass from the periodic table. I need the molar mass for what thing at this point? O2, yeah, because we're no longer at CO2, right? So with the stoichiometry, we are now at O2, so we actually now need to calculate the molar mass for O2. And if we do that, O2 is obviously 2 times 16, gets you 32 grams per mole. So we'll use that as our last step here, which is step number 4, converting our moles into grams using 32 grams per mole of O2. Thank goodness we didn't go any further. I ran out of space there. It is something. 4.36, I think. So we would end up needing 4.36 grams of O2 in this case. So basically what this says is if we want to produce in this reaction 12 grams of CO2, we would have needed to put in there, whatever we just got there, 4.36 grams of O2 for this reaction to produce that many. Pretty much all stoichiometry problems, no matter how crazy the equation looks, no matter how weird the numbers look, pretty much those 4 steps. You balance the equation, you take what they moles, you do the mole-to-mole relationship from the equation, which gives you the proper conversion factor to go from one thing to the next, and then you convert those moles to whatever units you want. Now, if something is done for you, you just go to the next step. So for example, if we started with moles, you don't need to unconvert it to reconvert it. You just move on to the next step and stuff like that. But pretty much every stoichiometry problem, those are the 4 steps you should always follow. Yeah. Yeah, so all 3 of these up here, these relationships, which are known as equalities or stoichiometric equality, they all come from the equation, and it really is nothing more than the actual coefficient in front of each of them. And we represent those as moles. And that's why really kind of the most important thing in stoichiometry is the equation needs to be balanced, because if you don't have a balanced equation, when you get to this part, you won't have the right mole-to-mole relationship, which means you'll never get the right answer. So really the most important thing is actually that very first step that sometimes people overlook. When they see an equation, they just assume, oh, it must be balanced. They gave me an equation. So you definitely want to make sure it's balanced. Otherwise, everything else will be incorrect along the way. And as you can see here in this particular problem, we only needed 1 of the 6 conversion factors, which is typically the case. And in most problems, you don't write all your options. You could just focus in obviously on the two things that you're interested in. Any questions on that? Now, also something that people sometimes think you have to do in stoichiometry problems is you have to sort of cross the arrow. And what I mean by that is people think that you always have to kind of do a relationship between, say, a reactant and product, and you don't. So you definitely could do a relationship between a reactant and product. You could also do it from a product to a reactant. You could also stay on the same side of the arrow and do the exact same relationships between two reactants. You could also, if you had two products, do the exact same relationship between the two products. So you don't necessarily always in a stoichiometry problem have to cross over the arrow to kind of do it. Sometimes you will stay on one side or the other, but it's still really basically these 4 steps. Any questions on that there? All right. So this is pretty much what we just went over, I think. So why don't we try one here and see what you come up with. So let's start with actually just the first question here. So let's go just this one for this part. We'll do the next part in a second. So we want to know if we take lithium metal and react it with water to form hydrogen gas and lithium hydroxide, how many moles of H2 can you form with the reaction of 5.32 moles of lithium? All right, so take a few moments here, follow the 4 steps. By the way, I did them in parts. You could do it all in one calculation if you want as well. That's perfectly fine. You can just put them together. If you do it in parts, again, remember, try not to round until kind of the end if you kind of get answers after each step along the way. But if you want to do it all in one calculation, you could absolutely do that, which they probably encourage here, but I don't really care. You can do it either way. All right, so in this case, we don't have an equation, so we'll talk about it here before we get started. Lithium metal is Li, yeah. Reacts with water, which is H2O, right, to form hydrogen gas, which is H2, right, plus some lithium hydroxide. So that is the equation that you should get. Now you follow the other 4 steps there. Which means you might need to balance it, yeah. Okay, let's take a look. So again, this is a stoichiometry problem. So we're just going to follow those 4 steps. And the first one, again, is to balance the equation, which in this particular case, we do need to do. We started actually, again, with stuff in words. So again, we just wanted to make sure we got the right formulas down if that should happen. And now we need to go balance it. And if you balanced it, I think we just need to lay up some 2s, I think. Maybe all through there. I get all the 2s there. 2, 2, 4, and 2. Yep. So that should be the balanced equation at this point. The next thing that we want to do is take whatever they gave us basically and convert it to moles. So in this particular case, we are starting with 5.32 moles of lithium. That means in this case, we don't need to do number 2 because it's already good to go in terms of the units. So that guy has already been converted, so no need to unconvert it or anything like that. The next step is really, again, the stoichiometry step, which is the mole to mole relationship. Again, that comes just directly from the balanced equation. So you basically want to find the 2 things you're interested in. One thing you're interested in is basically what they gave you. So in this case, they gave us lithium. And the other thing you're interested in is what you're trying to find, which in this case is H2, which is over here. And again, from that, we could basically get the mole to mole relationship, which once again is nothing more than the coefficients. So that basically tells us for every 2 moles of lithium that we put in there, we get 1 mole of H2 out, which once again could give us 2 conversion factors, which you don't necessarily have to write here, but we'll just again remind you, we could either have a conversion factor such as this, lithium on top, hydrogen on the bottom, or you could do hydrogen up on top and lithium on the bottom. In this case, You do not. So that's what we were talking about a second ago. So for example, in this question, we do because we're on opposite sides of the arrow. But if this question was something like, how many grams of water would you also need? Then you would just do it between, it would be 2 and 2 in that case. Or for example, if it told you over the arrow, better the other, and reactants, products, or stay on either side. Yeah. Other questions? Okay. So in this case, we obviously want to get rid of lithium, which means lithium needs to go on the opposite, which means we do need to use really this version here of the conversion factor. That puts us our 2 moles of lithium on the bottom, our 1 mole of H2 up on top. And again, this is really the stoichiometry part, this big step right here, which is just a conversion. We're going to get rid of the moles of lithium. And basically, we're just going to divide 5.32 by 2. Gets us 2.66 moles of H2. And in this particular problem, we are actually done because we were looking for moles, right? We were not looking for grams. If we were looking for grams, you would then do the 4th step, which would be moles to grams, in this case. So obviously, in that case, if we were looking for grams, which once again, we were not in this case, you would use the molar mass of H2, which you could get from the periodic table, and you would multiply that basically by the molar mass. It gets you about 5.36 grams of H2 in this case. So for the question, the way it was written, that is obviously the answer there, the guy in the box. Again, that would be step 4 if you needed to do step 4, but you really didn't in this particular case. Any questions on that there? By the way, this is how much product that we would be produced based on starting a material. So this is sometimes referred to as the theoretical yield. The theoretical yield is how much product you would make based on the equation, how much reactant you start with. This would be the theoretical yield in moles. This would be the theoretical yield in grams. So to answer sort of the question that was asked, if we did have, say, something a little bit different, let's just say, for example, we'll just use this number here. If we know that we produce 2.66 moles of H2, we could now figure out how many, say, moles of lithium hydroxide we would have produced as well by basically just following the same steps. We already have the equation. It's already balanced. In this case, we already have our guy converted to moles. If we started with grams, we would then need to convert it to moles. But at this point, you could do the same sort of relationship. So you go 2.66 moles of H2. And now between H2 and lithium hydroxide would be what we would want to look at if we were doing this problem. And this would be 1 mole of H2 on the bottom, gives us 2 moles of LiOH there on top. And that actually will take us back to 5.326, I think. So that will take us now to 5.32 moles of lithium hydroxide would have also been produced in this reaction. And that would have been the theoretical yield of lithium hydroxide. And once again, you could have used the molar mass of lithium hydroxide to figure out how many grams that would have been as well. So again, you can really do these relationships with anybody in the equation. And again, you don't have to go one side or the other, however you want. But as long as you know basically one piece of information about somebody in the equation that you could convert to moles, you could pretty much figure out everybody else in the equation by using these relationships. Any questions on that there? Okay, so why don't we do the second part of this question, which is, we'll just do the second, leave it here. I'll clear this out, I think. So let's do now here. So we already did this part, so we'll scratch that out. All right, so of H2 I mean, if you read 1.75 grams, clearly it's the same equation that we just used. Yeah, so same one that we started with. Let me give you some numbers that might be helpful here. Lithium is from the periodic table 6.941. Hydrogen 1.008. Oxygen 16. I think that's everybody, I believe. All right, so take a few minutes again, starting with the exact same. Okay, let's take a look and see how we're doing. So once again, we just want to follow these 4 steps. So obviously we already balanced the equation previously, so we're good to go. In this case, we are given 81.75 grams of lithium. We do need to do step number 2, which is converted to moles, so we get everybody in the right units. So we just need to go to obviously our periodic table here and get the molar mass. Once again, we're going to put grams on the bottom so that they cancel. This gives us 6.941 grams per mole of lithium. The grams here would cancel, and this would be sort of step number 2 there. Now, if you want to get an answer at this point, you can, or if you want to just continue on with the calculation, you could do that. So that's what I'm going to do here, just again to show you just sort of one calculation. At this point, if we stopped right here, we would be in units of moles of lithium. Once again, we're not interested really. Yeah. That's a good question. So the 2 there is really the sort of stoichiometry of the multiple relationship. Whenever you calculate molar mass, it always is just based on the formula, regardless of how many coefficients there are in front of it. And that's because the molar mass is always per 1 mole. So basically, you just do it from the formula. The reason, more importantly, you would not want to do that in this particular case is we're actually going to take that into account in the next step. So if you do it here and then do it in the next step, you're definitely going to be off and stuff like that. So the thing to remember for molar mass, it is solely just based on the formula. Just take the formula out, and regardless of what number may be in front of there. Other questions on that? Okay, at this point, we do want to go and do step number 3 now, which is our mole-to-mole relationship. And once again, that is what's going to allow us to go from lithium, which was given to us, to H2 here, which is really what we're interested in. So in this case, it happens to be the same relationship we had on the previous problem. For every 2 moles of lithium, we get 1 mole of H2. And again, that's just coefficients. Once again, we're really just going to use that as a conversion factor. And in this case, we want to get rid of lithium, which is on top. So lithium needs to go on the bottom, opposites to cancel. So we're going to go 2 moles of lithium on the bottom and 1 mole of H2 up on top. The moles of lithium here will cancel. And that basically would be step number 3 that we just did there. Once again, if you get an answer, try not to round at this point. By the way, if we did get an answer here, that would be the answer in, right? We're looking. But in this particular case, we're not looking for moles. We are looking for grams. So we do need to do the 4th step, which is now go from moles to. In this case, we also need to remember that we just did the stoichiometry, which means we now need to get the correct molar mass to do that with, which is actually the H2. So we got to get the H2's molar mass in this case. And once again, that would be 2 times 1.008 from the periodic table, giving you 2.016 grams per mole. And we'll use that as our final conversion here. Once again, moles are going to go on the bottom and the grams will go up on top. The moles of H2 will now cancel. And basically, we're going to multiply across the top, which is 81.75 times 2.016. We're then going to divide by the bottom, which is 6.941 and a 2, I think. Going to give us 11.87 grams of H2. And since H2 is a product, any product that you calculate from the equation is basically known as the theoretical yield. By the way, a yield is a product, and that's what the arrow means. It means if you can yield what's ever on the product side, you cannot have a yield that's a reactant. So yields are only products, and theoretical yields are basically calculated from the actual equation. First off, up to step number 4 we did there at the end. Hopefully you can start to see a pattern. Basically the same 4 steps all the way through. And like I did here, you could absolutely do it all in one calculation if you like to do that. Or I don't really care. You could break it up into parts as well. So either way as you want to do it. But basically what this says is in this reaction, if we threw in there 81.75 grams of lithium, everything went perfectly, no side reactions, nobody dropped anything on the floor or broke anything along the way. You should, in theory, make 11.87 grams of H2, which is why it's known as the theoretical yield. In theory, that's how much should be produced in this reaction. Any questions? Yeah. That's the molar mass of H2. So basically, after step 3 right here, the units we were in were moles of H2. But the question really wanted how many grams of H2. So it's basically a conversion between moles to grams, which uses the molar mass from the periodic table, which is this calculation right here. So that's, we use it because we have transitioned from lithium that we started with to H2 through the stoichiometry part. So we're no longer talking about lithium. If your question is, why didn't we use the molar mass of lithium at the end or something like that? And it's because at the end here, we're actually over to now H2. So we have to use its molar mass to convert it to grams. Yeah. Yeah. Other questions on that? Okay. All right, so let's try another one here. It's here somewhere, I'm sure. There we go. There. All right, let's do this one here. If we started with 765 grams of C6H12O6, what is the mass of CO2? So we're looking for how many grams of CO2 in this problem. Once again, we'll give you some numbers here. It'll be helpful. Carbon is 12.01. Hydrogen still 1.008, and oxygen still coming in at 16. All right, so again, a little bit bigger sort of formulas in this equation, doesn't really matter. Bigger numbers as well, doesn't matter. Still the same 4 steps, and see what you come up with here. Okay, let's take a look. So once again, going to follow our 4 steps. So first step is balanced equation. In this case, it is already balanced for us, which is good. Second step is to take whatever obviously they gave us and convert into moles, which in this case we were given C6H12O6. So we definitely need to do that. In order to do that, we need to go to the periodic table, get the molar mass of that big guy there. So that's going to be 6 times 12.01 for our carbons, plus 12 times 1.008 for our hydrogens, plus 6 times 16 for our oxygens. That's going to give us a molar mass of 180.2 grams per mole. Again, we're going to use that as a conversion factor to convert the grams into moles. So on the bottom here, opposite needs to go grams. So that's 180.2 grams per mole of our C6H12O6. That basically would be step number 2, converting into moles. At this point, the grams will cancel, and we are left right now at moles of the C6H12O6. That would then lead us into step number 3, which is really the stoichiometry part. So once again, we're going to go to the equation and find the 2 things we're interested in. So we are interested in this guy, which was given to us, and we're interested in CO2, which is what we are trying to find. Once again, we're going to get the stoichiometry from that, which again is just the coefficients. So that means there are 1 mole of C6H12O6 gives us 6 moles of CO2, simply just the numbers in front of everybody in that balanced equation. Once again, we're really just going to use this as a conversion factor. So once we go into here, we're going to go opposite. So we want to get rid of the C6H12O6. So that needs to go on the bottom. So 1 mole of C6H12O6. Up on top needs to go 6 moles of CO2. And that step right there is our third step, and really the stoichiometry step, which, as you can see, just a conversion factor. Going to get rid of the moles of the whole thing. And now we have successfully moved from the C6H12O6 to the CO2 in this case, which again is what we're looking to do. If we again wanted moles, we're pretty much done. We would just get the answer at this point, right? Because we're in moles, but we do want grams. So we do have to do step number 4, which is that last conversion of taking, in this case, moles back to grams. Remembering once again, we're now no longer at the original guy, but we're at CO2. So we need to go back to the periodic table to get the molar mass of CO2, which is 12.01 grams per mole, plus 2 times 16, giving us 44.01 grams per mole, which once again, we're going to use as our sort of final conversion here. What we have right now in our calculation is moles of CO2 up on top. So to cancel it, we're going to go opposite and put the moles of CO2 on the bottom, and the 44.01 grams of CO2 up on top. Moles of CO2 will cancel. And at this point, we would take 765 times 6 on top and times 4401. We then would come back and divide by 180.2. Going to get us, step 4, going to get us 1121 grams of CO2. In terms of significant figures, really should be looking at this number, which has 3, which means maybe we should take this to 1120 grams of CO2. This, once again, because CO2 is a product, would be our theoretical yield. Any questions on that? Again, you could do each of the parts separately and get an answer. Just don't round along the way. Or again, you can put it all together like we did with this problem. Question on basic stoichiometry problems. Again, hopefully you can see the pattern. It is just those 4 steps, and just follow them in order. Should lead you to the end, the correct answer. Any questions on any of that there? Okay. I think